Recall that we define an algebraic function field as a simple extension. Here, x and y are in algebraic relation, like in the elliptic function fields, or this equation can be defined with respect to other type of equations. And in the beginning of this lecture, we motivated ourselves one of the question about the composition of a function in reducible factors. But I also want to mention another motivation in this course, which comes from the algebraic coding theory. If you are not familiar with this theory, simply for the moment, you may suppose that our aim is to construct some finite dimensional vector spaces. Vector spaces over FQ. Due to the applications, we want to consider the base field as FQ with some desired properties, but whatever that means. But one of the idea to construct the finite dimensional vector space to use the space of the polynomials of degree at most n, and we can construct a vector space evaluating the polynomials in this vector space at given some distinct points. So for instance, if you consider the basis of this vector space, and if we are given n distinct point in FQ, it will be defined a place corresponding to the residue class field, and by looking at the evaluation of each function at given point, we may consider FQ span of these rows, and we may construct these vector spaces. And here we also want to understand, is it possible to evaluate some functions instead of polynomials at given some points? But in order to understand that, our base will be to evaluate a function z at given point A. But what does point mean? And regarding these two motivations, we introduced two notions. One is called the discrete valuation rings and the places. We consider their properties, and particularly the generator of the place will be called prime element and will play important role in the representation of the functions. And to understand the point, we introduced the residue class field as a quotient ring OP modulo P. And by regarding the relation OP and P with the base field K, we have observed that we can view this field, that field, as an extension of the base field K. And this extension degree defines as what we call the degree of a place. And we have also observed that it is bounded above the extension degree of the function field f over k of x. This is always finite. So here x and p. And the idea of the proof, we consider linearly independent elements from the residue class field. We may consider it as basis. And we can see that in that these corresponding functions are linearly independent over k of x. Here, these are linearly independent over k. And we have defined a point or the rational place as degree 1 places. Still, we don't know if there's a degree one place, sorry, in an algebraic function field, but at least we know that the set of places are non-empty. So that means we may consider such a structure. Then, depending on the residue class field, we define the residue class map and the notion of evaluating a function at a given place P. And as I mentioned before, the observations, the set of places are non-empty, and the reason is that every transcendental element is at least 1, 0, and pole in PF. So that means there exist the places P and Q such that VP of Z is positive and VP of Z is negative. And the other thing, we also introduced the discrete valuation maps. It's a kind of measure, it's the kind of tool that measures the multiplicities of the zeros and poles. So this is the zero order, and it's called the zero order. And here, the positive integer m is called the pole order of x. And particularly regarding this statement in the discussion session, we have observed that in the rational function field, when we consider the transcendental x, it has 0 at the place generated by the linear factor x, because VP of x is 1. So this means it has a 0 of order 1, or in other words, x is prime element for Px. And we also see that this transcendental has also pole, because we know that P infinity has generator x inverse, and we can write x as its double inverse. And similarly, if you consider the function 1 over x minus square with a constant a and k, now in this case it has a pole. It has pole at the place px minus a, and in this case it has order 2. And in the second, and to see that it has a 0 at p infinity of order 2, we can rewrite this function as the square of the prime element of the p infinity times a unit in the corresponding valuation ring O infinity. So this is why we can see that it has a 0 of order 2, because the valuation of this function is 2. And the other observation about places, we conclude that there are infinitely many places in an algebraic function field, and we concluded by the weak approximation theorem. And the other observation regarding this statement, so here we claim that every transcendental at least 1, 0, and 1 pole. But the other question, do we have finite many or infinitely many poles and zeros for a given transcendental? And we will answer this question in next 2 lectures. And we will see that every transcendental, actually every function, has only finite many zeros and poles. And we will be able to see this statement by giving a lower bound for the extension degree in terms of the number of the places, which are zeros of the or the poles of the given function. Or in other words, we can bound this number of zeros above by the extension degree of the function field. And this statement, in some sense, actually not some sense, will be generalization of the proposition 1.1.15 when we see that every place has a finite degree. So this bound will be a slightly generalized version counting the multiplicities of the function at the given place. More generally, we will see that in the given function field f over k, if we consider the set of zeros of a transcendental x, then this integer is bounded above the extension degree of f over k, of f over k of x, and this is finite. And then we can conclude that. So here, let me suppose that if we have infinitely many zeros of a function, then this quantity will be infinity, but we will get a contradiction of the finiteness of the extension degree. So this is why we will be able to conclude that there are finitely many zeros of x. So in the next lecture, I will prove this. I mean, the proof is quite technical. The idea and the techniques based on the proof of the proposition 1.1.15 by using big approximation theorem, because we want to choose some functions in f which will be linearly independent over k of x, and this will be possible thanks to big approximation theorem. So in the next lecture, I will go over its proof for the spatial case when r is equal to 2. Okay, see you in the next video. Bye-bye.